Right here, right now, the time is now. Advanced thin films, we ask how. Not just performance, not just design. Can you build it? Built for the line. Layer by layer, step by step. Harder demands, higher specs. Advanced thin films, advanced thin films. Can you scale it up? Can you make it work? Advanced thin films, advanced thin films. Built for the line, built to deliver. Higher demands, tighter control, complex multi-layers built to hold. Monitor the process, measure it right from design to yield, from lab to line. Where are the bottlenecks? Where do tools fall short? What must change now to move it forward? Advanced thin films, advanced thin films. Can you scale it up? Can you make it work? Advanced thin films, advanced thin films. Built for the line, built to deliver. Monitor it now, measure it right. Design to scale, build it for life. Suppliers, makers, one value chain. Build it once, build it again. Advanced thin films. Advanced thin films. Built for the line. Built to deliver. Advanced thin films. Advanced thin films. Can you scale it up? Can you make it work? Advanced thin films. Advanced thin films. Built for the line. Built to deliver. Advanced thin films. Built for the line. The discussion starts Tuesday, April 28th, 2026, at the Optica industry meeting. Built to deliver.
Начали. Алло.
The next Optica online industry meeting is a live discussion on advanced thin films. Thin films are not short of ambition, The question is whether industry can manufacture that ambition at scale. Across photonics, optics, defense, semiconductors, high-power lasers, sensors, and VR, AR, the question is becoming more direct. Can these technologies be monitored, controlled, measured, and produced reliably in the real world? So this session is not a celebration of technical progress. It's a discussion about the bottlenecks. Where do current solutions still fall short? What do advanced applications now require from deposition equipment, metrology, process control, and design workflows? And where does the industry still need much tighter coordination across the value chain? We're joined by experts from across the field, including Edmund Optics, OTF Studio, Research, Opcos AG, Biller Group, IDEX Optical Technologies, Essent Optics Europe, and Corning. And the focus will be practical: process monitoring at scale, equipment for complex multi-layers, design for manufacturability, and advanced characterization and metrology. So let's see who's live in the Zoom room.
Advanced in films, built for the line, built to deliver.
Build to deliver. Welcome everyone. The time has come. We are here. It is today, 28th of April, to talk about thin film technology. We're going to talk on the next 90 minutes. We're going to talk about technologies that allow us to do beam splitting, filtering, to allow us to put high power through optics. We're going to talk about the key technologies that allow optics to go to the next frontier. And we had the best of the best to cover those topics. I would like to say, first of all, this meeting is an online meeting. This is not a webinar. If you came today here just for the interest of listening to very interesting presentations, you will, but you will not get the most out of this. Today is a meeting to answer the Optica question. What can you do for others and what others can do for you? And allow me to first say thank you to the people who made this meeting possible for everyone. Thank you very much, OE Waves for sponsoring today and making this meeting free for all the people here who are here to do serious business. As usual, this meeting brings together two teams of companies. On one hand, we had the integrators. These companies that came here with a shopping list. They are looking for more thin film technology to incorporate to their solutions. Those are IDEX Optical Technologies and Edmund Optics. And then we had the enablers, those who came with a solution that can fit the market demand. OTF, Research, Opcos, Buller, and Essent Optics are here to cover that particular gap. These are all Optica corporate members. If you want to be part of this community that connects, join corporate, optica.org/join corporate. There you have the application form and all the benefits. Today is about optical thin films, but in a couple of weeks, on the 12th of May, we talk about high volume packaging of photonic integrated circuits, and then afterwards we have an industry tutorial on heterodyne laser mixing, sponsored by Indie. Then we have on the 2nd of June, photonics in the energy world, energy fusion. And on the 23rd of June, we talk about 3D sensing. When we go for a couple of weeks on holiday in summer, and we come back on the 25th of August. We talk about ophthalmology, applied imaging, aerospace, quantum safe networks, mixed reality, new space, quantum computing, and co-packaged optics. If you want to participate in any of these events, if you want to show your technology at any of these events, or you want to sponsor any of these events, contact us as soon as possible. This platform is for you to sponsor and participate. I also would like to say that in only 5 weeks, all of us are going to Brussels. We're going to Brussels because we celebrate the Global Advanced Manufacturing Alliance annual meeting. There is where we meet, all of us, to talk about what we can do for each other. Do not miss 2nd and 3rd of June in Brussels, sponsored and hosted by Photon Hub, the Optica Global Advanced Manufacturing Alliance annual meeting. I also would like to say that afterwards we go to Glasgow for a Quantum Industry Summit. After summer, all of us go to Malaga for a flagship event, the Global Photonics Economic Forum. And on the 9th and 10th of June, we have our Optica Industry Summit on advanced aerospace and defense technologies. These are our upcoming events in Europe Write the dates for those. I would love to see you face to face there. And I would like to say also today is all about advanced thin films. This meeting is live streaming YouTube. So let me say hello to the YouTubers on the world. Hello, YouTubers of the world. If you have any questions or comments, please write them in the chat and I will read them in the room. And this, of course, also valid for the people here with me in the Zoom room. Over the next 90 minutes, if you have any questions or comments, write them in the chat and we'll make sure your voice, your technology live for everyone to understand what you can do for each other. Let's start today. Olga, congratulations on the great agenda you have put together. I'm looking forward to welcome our opening speaker today. He is Darren Burns, the CEO of FIDEX Optical Technologies. Darren, thank you very much for joining us today. The floor and the attention of everyone is yours.
Well, hi there. Welcome, everyone. Thank you for joining. I think today hopefully I'll just set the stage for some high-level topics, and then individually I think we'll see comments from various other folks on the panel that may help you appreciate kind of where the industry has been, where is it headed, and maybe how things have stayed the same, and maybe how things have changed. So, with that in mind, let me move to sharing. Get the right button. There we go. I get to be the first one. Okay. And present. There we go. Okay, can everyone see that?
Crystal clear.
Okay, so I am from IDEX Corporation. IDEX is quite a large company. If those of you who know us or maybe don't know us, but we are an industry solution provider across a whole variety of technologies. But in particular, we have a group of businesses that we call optical technologies, and that group of businesses has long been and participated in the optical thin film industry. In fact, some of the names that you might recognize are Semrock. Advanced Thin Films actually is a company name, which lines up nicely with the title of the talk today. Iridian Spectral Technologies, and CVI Melis Griot businesses from historically from the past. So all of those businesses are part of IDEX. Now what we're calling materials science solutions, and really the goal there is because it all sort of links together to provide solutions into the space. So I did a little thing, right? And I first said, hey, Anthropic, well, Perplexity in this case, right? Search for advanced thin films over the past 3 decades and give me at least 100 references by decade, and then tell me what are the top words that pop out. Right. So this is I skipped the middle decade here because it's just sort of the transition. But you know, a lot of stuff here you'll see are things you'd expect. Obviously, optical pops up in a lot of places because advanced thin films for a very long time, at least multi-layer films, have been in the optical domain. Materials, sputtering, CVD, etc. You see a transition. Right, we're starting to see more ALD references in the latest decade than maybe we had in the past. There's a good reason for that. I'll come back to that. But many other things, right? It's not just the process itself; it's the characterization of the films. It's also the how do they survive the environments that you put them in. So durability, adhesion, these are all super important things. And I think the main message from a lot of this is that there's some things that have changed, but a lot of it hasn't, right? So if you look back at what was being done in the late 90s to what we have today, at least in optical thin films, there are some significant differences, but there are also a lot of things that have stayed the same. And you know, for those of you who were actively around in your careers in the late 90s, we'll all remember that the telecom, datacom boom and bust kind of happened in that time period, moving into the early 2000s. There are actually a lot of deposition technologies that were developed during that time frame, or at least commercialized during that time frame. So, in particular, ion beam sputtering was a technology that had a foothold in certain areas, such as low loss film environments for things like ring laser gyroscopes, where you had multiple bounces off of individual surfaces, and you needed to have things like a few parts per million total loss off of high reflectors. Well, that was a hit the sweet spot for ion beam sputtering. Well, and then it became an advanced technology for multi-layer coatings for datacom and telecom. But taking that a little bit further, right? If you think about the title up here, different applications require a different, I'm going to say, balancing act. And so what you're looking at here is different applications or different sort of incarnations of how do optical thin films or advanced thin films find their way into photonic applications. And then the two sort of graphs on the right are essentially the variables. So this is sort of how we look at it. The variables that are important when you think about advanced thin films. And then the middle graph is really against process technology, and the bottom right graph is against markets. And in this case, I chose the 4 markets that are most important to us at IDEX. But if you kind of look on the left, different application space, clearly there's the need for focusing systems and long transmission of data and energy, and I'll chat about that briefly on the next slide. Components themselves that have either integrated thin films or thin films externally. This is an area we actually do a lot of business in, and the industry sees a lot of need for, and that is integrating thin films inside of complex optical assemblies. Filters and wavelength control, always important. Laser beam combining is important, beam shaping, etc. And then I'd say we've seen more direct application in the last decade, really, of nanostructured surfaces and how do those surfaces either combine with thin film, multi-layer thin films, or replace them. But if you kind of look at the charts, right, there's no one perfect solution, right? And I think that's a really important thing for us to think about as we walk through the rest of the discussion, because all these things matter, right, depending on what you're trying to do. Stress is a huge thing, right? Sputtered coatings are great for process stability. They're great for high density, predictable material properties, but they also come with a lot of stress, right? And you have to manage that stress. Different materials are critical depending on the different domains you're working with in different wavelength spaces. I talked about low losses, low defect densities. Sometimes the speed at which you can deposit films over large areas really matters, and in some cases just the size that you're coating matters. And so at the end of the day, we have within IDEX, we have access to all of these technologies for this very purpose, right? Because we can't just sort of hone in on one specific technology or process. And then the last thing I would say about this is, depending on market, you also see significant differences, and I'll give two just examples real quickly. For the work that our team at Semrock does, it's almost a situation where if you could just take the film, the multi-layer film stack, and remove it from the substrate, that would be better, right? That would be better for a lot of the industry. If they could just take the stack, the filter, and stick it on something and not have to deal with the substrate. But on the other side of that, you've got situations where you're trying to do beam shaping or beam delivery, and now the substrate shape and the material, they all really matter. And so the combination of the multi-layer films with the substrate is critical. And then characterization of that whole sort of system is really important. And lastly, I'll sort of go to one specific application because I think there's been a lot of energy on this and a lot of discussion lately. And that is what we're calling space data. So if you think about kind of where things have gone in the last, even the last few years, there's a significant need for moving information and energy around between the terrestrial environment and the space environment. So this is an area that we participate in at a very high level. But it's not just optical coatings, right? Like the coatings are really critical, but without the ability to put them on surfaces that also help with beam shaping and beam delivery, you kind of don't have the answer, right? The solution comes from the combination of all the things put together. And really this industry or this market is probably the fastest growing market for advanced thin films that we certainly see, because you can almost think of it as taking telecom into space. And so that's why we sort of use the term space data, because that's really where we're going, right? And if you've seen some of the last published accounts from the big players in the market, it was a crazy idea 6 months ago, or maybe even a year ago, to put data centers in space. It's kind of not a crazy idea anymore. There's a lot of money. Obviously, there's a few $1 trillion companies and a bunch of people with a lot of money that really think this is a viable alternative to trying to generate large amounts of energy on the ground, and cool data centers. You kind of get the advantages of a black body radiation environment in space. You get the advantage of massive solar arrays and radiators, and so it's not kind of not crazy anymore. But in order to do that, obviously the data has to find its way from the ground to space and back again, and you've got to be able to communicate between the different satellites and things that are there. And if you look at the last piece here I'll mention is, if you just look at the Artemis mission that just happened, right, sending humans around the moon and back again. All of the data communication that happened, the video, the communication with the International Space Station, all of that came about through, at least partially, through laser communication. And so there were laser transceivers and receivers on the Artemis aircraft, and that you can sort of look that up and see publicly what was discussed on that topic. But that was kind of a next generation step for NASA that they had started, 20 years ago or so, right, in that general area of interest. So I'm gonna stop with that, because I think that's probably getting close to my time. But I would just leave it with this, and that is, advanced thin films have been critical in multiple markets for a very long time. And they just continue to be. We've done, every year we've done an analysis to understand, are we going to end up replacing multi-layer stacks for filters and for beam delivery applications anytime soon? And I just don't think the answer is yes. I think it's going to be around for quite some time, and the combination now of making physical changes to surfaces, as well as applying thin films and thin film stacks to those surfaces, will continue to be a need and an industry for a long time to come, in our opinion.
Thank you, Darren. Darren,
Yeah.
if we're already talking specifically about the space market, and for the technologists in the room, what would you pinpoint as the major challenges for this specific application? Like coatings for
Yeah.
laser-like communication in space.
So it's from keeping on the topic of advanced thin films, right? It's sort of the same set of problems that we had during datacom and telecom, right? You're trying to put as much data as you can in a transmission beam, in this case. So it's a free space beam. You can't run a fiber from space to the ground. So essentially you're transmitting that data through a singular beam. So now you've got a bit of an issue of trying to maintain a focused beam through that long pathway, because you can't just launch it into a fiber and then expect the fiber to do all the work in the transmission. So it's how much data can you combine, right? So again, wavelength division multiplexing is still a thing. It's not quite at the level of density that you would have seen in the telecom days, or even today within telecom, but it's still there. And then the other part of it is you've got this sort of natural conversion from free space to solid state and back again, which are a lot of the same challenges we had before, but now everything's happening in space as well, right? So the environment is different. Optics have to survive launch. They have to sort of live within these environments. And you've got, you got different things that happen between the different orbits. So geosynchronous orbit, different things are happening, and the environment's different than it is at low Earth orbit. So all those things matter and present a different sort of array of balance to those variables that I mentioned earlier.
Are there any specifics, for instance, for the design of this multiplexers? Because you have to probably calculate with the vacuum shifts and everything, and it's a very deep vacuum.
Yeah, it's the same set of problems that we had and solved for with datacom and telecom. So I would say from a design standpoint, it's not a huge lift compared to what we've all known and had for a couple of decades. The real challenge is how do you take that and now put it into a different environment? So now everything is maybe not hermetically packaged in the same way that it is in datacom and telecom. Obviously has to survive launch, has to survive in space for that period of time. The level of multiplexing is not as compact or as dense as it is terrestrially. But stability is critical, right? So you mentioned that at the end. If you're moving from vast temperature differences and vast exposure differences to different radiation, that's important. So a good example is you kind of have to block out sunlight, right? You can't deal with sunlight, and you have to block it out to a pretty high degree. Something like OD 7-ish, right? To get rid of the sun relative to the laser light. So those are all industry level challenges that have been around for space sensing environments for some time, but now applied in a much higher volume, sort of higher impact in terms of on time and data coverage over large areas and large time than maybe you have with a focal plane array where you're sensing Earth observation, but it very similar.
Maybe a little bit of the provocative question, because let's say around 4 weeks ago we had a optical industry summit at Corning about microstructured optics, and specifically microstructured components. And some of them, like the meta lenses, right, they are proposing themselves as an alternative for conventional beam splitter or conventional beams, conventional optics and optical coatings. What would be your view on this, or your touch?
I think the hybrid is really where we're going to end up, where it's a combination of multi-layer interference stack coatings for very complex spectral control over angles, over polarization, etc. And maybe in more complex environments that you have to survive in. But there's a natural path, I think, to combining nanostructured surfaces with thin film coatings. Much like you see with things like high power grading systems, right, where the grading is built into the top of a multi-layer stack, right? You could imagine that kind of a scenario happening across the board with this. But it's been true that we've been talking about nanostructured coatings or nanostructured layers, we'll say, for quite some time, and I think it really just depends on the application. High power is an area where there's still an issue if you're transferring energy and not just data. Then you've got to have materials that can survive those environments and can survive really high laser fluxes, and that's still going to be a challenge, I think, for some of the nanostructured surfaces.
Since we're in the industry meeting, what do you think? What if you need a support from for IDEX from some of the partners? What do you think would be maybe a partnership or collaboration that would make the most difference for you?
Yeah, so it's sort of a lot of the same things we talk about in some of the other photonics areas. Characterization continues to always be critical. We take that on as a challenge for ourselves in our own manufacturing environments, is how to create closed feedback loops on the process itself, so that we can modify and control the deposition of multi-layers while we deposit them. So that's really critical for us. But having said that, many of the tools, the process equipment, even the characterization equipment, is not necessarily built for this end application space, right? It gets used for this end application, but because the volume of tools sold into the industry is a lot smaller for advanced thin films than it is for, say, semi, where you're maybe doing 1 or 2 layers, and high vacuum equipment, or even characterization, right? A lot of the spectrophotometers and things that are built for the industry are built for those other application spaces where there's just higher volume and they can sell more tools. So continuing to look at in situ characterization, I think, is really important. Ideally, you don't want to have to go through a complex process and then find out at the end that you had an issue. So how does the industry solve for that, right? Basically, closed feedback loop on all processes associated with advanced thin films.
Okay. Thank you so much. And I think I asked you, of course, with a purpose, because one of our partners and one of our speakers in the room, and OTF Studio, they also have a solution for exquisite in situ thin film monitoring. And so I would like to hear from them if they have something that they can report, and then maybe that potentially to support you in your endeavors. Thank you so much, Darren. Thank you for your touch on what is actual in the thin film coatings. So, Tatiana, OTF Studio, so you've heard the challenge. It's the in situ monitoring, how OTF can help.
Hi, so we have a special product, Tareo. It's can be used for assistant and automation of thin film deposition. It can be used for analysis, for online analysis, for online characterization, and online reoptimization if it's required.
Do you have it in your slides, Tatiana? So just share and tell us what OTF can offer.
So I show now my slides. So.
Can you go to the presentation? Can you go to the
Yes.
presentation mode? Fantastic.
So it's okay. Yes.
Yes.
Yeah. So we are OTF Studio. We are in Germany, in Garching by München. So this is a small town near München. And in this picture, you can see Neuschwanstein. This is a castle near München. And this is a silhouette of this castle. And even such complex spectral characteristics can be achieved with our thin film software. So our main product is OTF Studio thin film software that can be used for design and evaluation of multi-layer coatings. It's not only spectral characteristics or phase characteristics, it can be also electric field, stresses, integrated characteristics, color properties. Also, we can characterize monolayers and produced multi-layers based on measurement data, based on different kinds of measurement data, online and offline, ellipsometric and photometric. Also, we can provide optical monitoring, so we can generate, automatically generate monochromatic strategies. We can generate monitoring spreadsheets. Also, we have different visualization tools like plots, like contour maps, like 2-dimensional, 3-dimensional plots. And of course, powerful COM interfaces that can be used for external calls of our software in your software. So you can control our software through your software through COM interfaces. Our software is modern, fast, effective, user-friendly, and we can optimize not only spectral characteristics, but also phase, group delay dispersion, thickness, stress in coatings, electric field, color properties, integrated values, and the software is aimed at different classes of coatings. It's of course precision optics like beam splitters, like anti-reflection coatings, high reflectors, dichroic mirrors, different kinds of filters, coatings for ultra-fast optics and laser-related coatings, also color coatings for color applications. And we have a special block for so-called EGU applications like architectural glass. So here we can see different challenging coatings like multi-line filter. Such filter takes about 1 minute to calculate. We can see stress compensation, we can see electric field compensation, optimization, color optimization. And of course, we have a large set of characterization tools of batch processing, batch import of data. And the product that Olga asked is Tareo. This is a library that can be used for assistance of depositions. So the software, you give the online data, online measurements, and in different ways you decide how the software can so characterize, analyze, and re-optimize your deposition process. So if you have questions, we have trial versions of our software, and we
Hi,
have
Tatiana.
different
Thank you very
types
much.
of-
It looks like great software. Who is your target audience? Are you selling this to equipment suppliers that manufacture volume testing of optics, or more like optics manufacturers? Who are the ones that you are targeting? They are all here in front of us.
There are different types. For example, it can be optics manufacturer of optical coatings. It can be a manufacturer of deposition chambers, deposition plants. It can be a manufacturer of architectural glass. It can be scientific institutes, for example, who
Let me
make...
have all of them are here and they are all looking forward to talk to you. But you didn't see the equipment suppliers. Sebastian, thank you very much, Sebastian Reithinger, for joining today from Alphamation. You produce equipment for the volume testing of optics. You do a fantastic job. Can you tell us a bit of what you do? And many people here who are in the room could be your potential partner suppliers and customers.
Yes, hello, Jose. Thank you for the introduction. It was not planned, but I can spare a few words about Alphamation. I do have a one slider if I can share quickly. So
Go
just
ahead.
to have a...
All the way from Monza, Italy.
So I should
Great
stop,
company.
yes?
Yes, we will stop your sharing. Thanks.
All right, you should be able to see my screen now.
Crystal clear.
So yes, we are located near Milan in Italy. I'm trying to put it in presenter mode.
It's okay like this, it works well.
Yeah, okay. So we are located near Milan in Italy, and we make automated test equipments for micro-optics and optoelectronics. And we are about 130 employees, and we have a lot of engineering capabilities in-house, ranging from optical, mechanical, software, electrical, and so on. So we build and we design the tester in-house, and we target many kind of markets, from consumer electronics, automotive, and telecom application with coupling optics, for example, and so on. So yeah, we look typically for opportunities to develop new test solutions. And yeah, if anybody wants to get in touch with me and with us to discuss functional testing, yeah, feel free to contact me.
Grazie mille, Sebastian. Definitely, Tatiana, as you can see, this is one key partner for you. Another one, we have here, had the pleasure of having Carlo Kosick-Williams from the company Corning. Carlo, thank you very much for being with us today. It was great to meet all your team when we had our industry summit at Corning, New York. Carlo, you heard the presentation from Tatiana on OTF. What makes you excited about this software? He's looking for the unmute button.
It's in your left lower
Okay,
corner.
I found it. Thank you. Yeah, so at Corning, just by way of introduction, I lead our thin films and coatings capability here, with the broad responsibility for the coatings for all of our various businesses. Um, we're always looking for, you know, the more optimal or the more updated tools that we can use for our design approaches. At Corning, we focus not only on the design and the tools that's used for the design, but also the new materials that we are developing. So for us, it's the materials that's the anchor, along with the process, and the design is the third leg. And so that third leg, the design and new tools that we can exploit, is always of interest for us. So that's my interest here.
Thank you very much, Carlo. Carlo, Darren, one of the things when it comes to the coatings is the testing. We already heard what Tatiana can do in the modeling. We heard Sebastian on the testing. Why don't we go to the spectrophotometer? So my friend Taras from Essent Optics. Taras, Acho, thank you very much for joining today. Can you tell us a bit what you do and how you can actually help so far Darren and Carlo and later many others?
Hello, everyone. Thank you very much, Jose, Olga, and Optica for this amazing opportunity to join this event. It's a big pleasure and privilege. I will share my slides.
They're almost here, coming all the way from Vilnius. They are not yet here. Here we come.
Yes.
Still not arriving.
We've done the tech test. They
Yes.
are arriving.
Yeah, they are. Okay.
Oh, here they are.
So once again, hello, my name is Taras. I'm from Essent Optics. We design and build spectrophotometers for characterization and inspection of optical coatings on flats, prisms, lenses, and even gratings. And in many cases today, the limitation is actually not the optical design, but the ability to measure it accurately. The message which we convey to the customers is that you cannot produce any better than you measure. So this is exactly where we focus. Here is the example of the extreme resolution invisible range. You can see that a very steep edge, which we can measure on the coating, the transition from 80% to 5% happens within just 0.2 nanometers interval, and which is very critical to measure and challenging, especially in the very low transmission levels. At the same time, we can, with our technologies, we can resolve very narrow spectral features. This example, actually the animation, shows a real result, real data taken from measurements. You can see that the bandwidth is below 1 nanometer value, and importantly, this is done without any smoothing or other modification of the data. So this is a real spectral shape we can get on the sample. We ensure broadband blocking up to OD8, which is also quite challenging. And these types of coatings are widely used in applications like, laser systems, Raman spectroscopy, LiDARs, and spectral filtering. We actually apply the same approach in spectral regions where conventional methods fail or struggle. For example, deep UV. This result shows measurement of optical mirror, high refraction mirror, optimized for 193 nanometers, and we achieve stable and repeatable results without complex setups where high stray light or low signal are typical. The coatings are critical for semiconductor lithography or other deep UV laser systems. If we go to long wave infrared, this is also a very challenging region where conventional FTIR systems are often limited. We go beyond that, enabling absolute transmission and reflection even at different angles and different polarizations. And all this done without reference samples with quite high repeatability. This image shows 11 measurements performed sequentially. This is typically critical for thermal imaging, for infrared systems, and obviously defense applications. All in all, to sum up, we are focusing on solving the most hard measurement problems in the optical industry, from sub-nanometer features to extreme spectral regions. Thank you so much.
Thank you very much, Taras. Thank you for being with us. It is
Yeah.
great to have questions for you. And the first one is coming from Tatiana from OTA. By the way, Tatiana, you have great feedback in the chat about your software. You must be very happy to be in the room with us. Please tell us what's on your mind.
Taras, one question. What is the accuracy in the UV and in mid-infrared ranges? How do you estimate?
Okay, we test all our systems using the NIST traceable reference samples. This is a standard procedure for us for every system we produce. The values which we get in UV and visible range, they are about like 99.95, 96% absolute reflection, even at different angles and polarizations. For long wave infrared range, we are going to 1 decimal point. So it's like 99.5.6%, and that's what it is.
Thank you.
Thank you. Thank you, Tatiana, for being here. So far, you have been a rock star today. Darren, you have your hand up and something good in your mind. Tell us what it is.
Yeah, so a couple
Darren.
things, right? So in terms of the tight measurement of say nanometer or nanometer class full width max filters, right? One of the challenges has always been how do you make that kind of a measurement without having a spectrally coherent source? And also you limit the cone angle essentially of the beam that's coming in. Are those the main approaches you're using here? And how do you sort of balance that out with the other characteristics, right? Of throughput into the system, et cetera. Maybe you can comment on that.
Darren, very, very good question. Thank you very much. And they are actually definitely from the industry. So beam collimation or very low divergence of the beam is very critical in this case. We have a beam divergence of about 0.2 degrees only in this system, which is capable to measure these sub-nanometer filters. Also, with a light source, we have a laser-driven light source. This is not a laser, but it's a high-power source which generates sufficient flux of radiation to the system. And as a result, we have very good signal-to-noise ratio. Given the specially optimized optical layout of the spectral photometer, we are capable to measure both in one system extremely nano band filters and coatings with high optical density, and this is broadband.
Okay. Are you doing so to get down to the sort of spectral bandwidth of less than a nanometer or so?
Mhm.
Is that something you're doing with like in traditional systems? You might limit the slit width in your sensor package, or you might change the spectral resolution of the source light. Do you do a combination of those two in your system?
I'd love to answer that there is one particular element which makes the whole deal. No, unfortunately, that's not the case. In reality, the whole design from the light source to the detector, that's really optimized for the whole system. We have very good sources. We have specially optimized optical layout of the monochromator. We have filters, we have slits. The whole setup, the whole design is tailored to measure coatings, not for chemical or life science applications, only for coatings. That's our focus already for 19 years.
Well, I'm sure we could nerd out all day long on the specifics here, but reach out to me. Let's talk and figure
Thank you
out.
Darren,
very
can I
much,
reach
Darren.
out to
Thank
you
you.
right now?
My
Darren,
pleasure. Thank you.
you gave a fantastic opening presentation, Darren. We have people in the room who are expert on laser optics, especially when it comes to high power. We have Krishna from the SLAC laboratory of Stanford. We have companies like iPhotonics, like Bueller. Could you tell us what you do in the field of high power and perhaps share a couple of needs that we could share with them?
Sure, yeah. So if you look at the genesis of some of our companies, in fact, the company that was called Advanced Thin Films, which is where I came from, we started that company with the intent of actually delivering high power laser optics to the industry. And so when you think about what does it take to have a high power laser optic and coating that fits with it, it all comes down to stability of the material properties and reduction of contamination and defects, right? I mean, that's the number one thing. So there's a reason there's been there's been a laser damage symposium for now on 40 years or so, right? The problem is not solved. And fundamentally it's because you're trying to balance out all these challenges, but still use a process that gives you extremely low loss. So ion beam sputtering is a technology that's been around for a long time as probably the primary process in that domain. And the reason is just because you can produce super low loss optical coatings with multi-layer stacks, right? You can have a couple hundred layers and still get a few parts per million of total loss. And when I say total loss, it's absorption plus scatter. Right, so you can get low absorption losses in some other processes, but sometimes you can't reduce the scatter because you can't control crystallinity. So this is another part of this, right? Is as you run the process and as you add layers on top of layers on top of layers, the individual layer characteristics matter, and they're not consistent often from the first layer to the last layer. So if you're doing deposition over the course of hours or maybe even a day in some cases. We do some coatings that are 500 layers, right, for certain applications, and so that requires extremely tight control of the overall process. But so I'll say PVD, right, is the world where often those high power laser optics come from, but in particular sputtering technology and very specific sputtering technology often.
Darren Burns, of course, the CTO of IDES Optical Technologies, and they're one of the experts worldwide on IBS. So I wonder if everything in IBS is already discovered. I'm happy to have in the room Vitaly from iPhotonics and Gianni from Bueller. Gianni, you came here with a new story, providing equipment for all thin film technology. Could you tell us a bit of what you do and maybe something that could help Darren and the rest of the people in the room?
Thank you. Happy to be here. I'm an R&D process engineer now with Bueller since 2 years, and my specific topic here is ALD. I've worked practically all my professional career in ALD and now with Bueller, and I'm here to present our high-speed ALD technology for conformal optical coatings. So I think Darren's initial presentation highlighted how ALD has come more important in literature recently for optical coatings and the unique challenges that we these days have for the coatings. And this is also Bueller, of course, I think many in this room know about our sputtering or PVD technologies, but more and more of our customers have applications where we require conformality that our existing techniques cannot provide. So ALD is used for decades in semiconductor industry, and it's known for the ability to coat conformally structures, microstructures, nanostructures, microstructures. So it can be a microscopic lens or a micro trench that you want to coat conformally. But also it has been known for being a slow method, takes long, and it's not has been not applied much in optics because of this limitation for especially when you want to do thick optical coatings. So our approach has been now go to spatial ALD, where instead of the conventional controlling ALD by time, we are controlling spatially. This allows us to get PVD level deposition rates and still maintain the benefits of ALD. So we can do coatings from nanoscale to tens of micrometers thick and still have the benefits of ALD. And our ALD project last year reached a big milestone. We now have our publicly available or ALD labeled optics ALD 1200 tool. So we started our ALD project with a lab machine, a small lab machine to understand the technology, followed by learning, doing sample coatings with it, and then going into designing our own machine for large-scale industrial production. So this machine has now unique possibilities. We can coat up to 8 300 millimeter wafers or other substrate size. Of course, it can be anything, but practically we are limited around these sizes. We can do double-sided deposition in a single run and up to 30 millimeter substrate height. With 4 precursors, 6 process gases, our optical monitoring system is also available similarly to our other machines, allowing very precise control of the optical stack. And we can incorporate this with a handling system. So to highlight some of the results or applications that you can think of in which ALD and specifically or spatial ALD could be beneficial for you is now we can talk about optical coatings on microscopic lenses. Of course, it's known that it's very challenging for PVD techniques to coat these kind of structures conformally. And it has been very challenging to coat such with ALD with a reasonable time frame and productivity. So here we had the cooperation with FISPA where we did coated some microscopic lenses with 20 millimeter height, 10 millimeter height, sorry, and 20 millimeter diameter. And we can show how we made a Bragg reflector 2.2 microns thick and could coat this lens very uniformly with a very respectable production rate. Of course, now we are getting into when we have waveguides, meta optics, then we go to a different kind of where we need to coat microstructures or where we need to maybe do a thick coating where stress control is very important. And with our plasma technology, we can also have the great benefit that we can actually control the stress very nicely. This is somewhat material dependent, but for our basic materials, we have very good solutions. So practically we can do a 5 micrometer thick coating stress-free, which is of course something that many other techniques struggle with. And this can be very important when you have for instance, maybe you want to deposit on a thin glass, maybe a thin structure where the bow management is crucial. Or of course the lamination. And similarly, trench fill. This is not a very complex, but it's our first example to show how you can do a thick coating and fill trenches nicely. So this allows us to achieve various types of microstructural coatings that are normally very challenging. I think that's, and I'm happy to answer your questions. And that was a brief overview what we can do, and happy to discuss more now. And of course, you can reach out to me later on. Thank
I
you.
believe there will be quite a few people reaching out to you. Carlo is interested. Darren, so you've mentioned that, okay, ALD has developed a lot. So what's your question?
Yeah, maybe just if you could comment, Yanni, on I mean so ALD. If those in the semiconductor world know, ALD is a huge process technology, right? That's used across
Yes.
semi right now. However, for this domain of optical thin films, it's kind of always been this. It'd be great if we could get it to work, but you know, where's the trade space? How many layers can we go up to? Like, is it ready for prime time for filters and these kinds of things? Obviously, you get the benefit of the conformal coating and lower stress, or at least control of stress. Can you just comment on, like, how does Buehler view this? You know, and if you were to compare somebody who's, you know, making filters out of your Helios system compared to, you know, now, where does ALD slot into that, you know, space between IBS and magnetron and all of the different processes?
Well, of course, for me, it's always about what are your key requirements for your process and limitations of your sample. So we see ALD as the technology that will be used for applications where you need this conformality. That's the big selling point. And of course, this stress management for thick coatings. And when you need to make the thinnest layers possible accurately. But it should be, in our case, this ALD also slots as a technique that, or spatial ALD slots as a technique that is suitable for doing multi-layer coatings, thicker coatings. So as said, in semi industry, it's well used. If you want to do a 5 nanometer perfect ALD layer, the speed benefit that our technique, the spatial ALD provides, is not a great benefit. Then you are looking for the highest performance on a single wafer, and that's a different topic. IBS then, of course, for the low loss coatings, I think ALD still has some work to do to get that. Has its unique benefits. So, and then of course we come to that of course our sputtering technology is a long time used technology. We have it very much in very established products for that. So in a sense that if you want to do complex or thick coatings with optical monitoring on flat substrates with high performance and good uniformity, then in this case, sputtering is maybe a more cost-efficient alternative.
There is always optimal. You've also mentioned about your optical monitoring, and I believe Tatiana has a question about it. Tatiana?
I have a question regarding temporal and spatial ILD on the first slide. Can you explain in 2 words what do you mean?
So
you got 3, Yanni.
Okay. So in temporal ALD is what is the most typical ALD process. You have a process chamber and you pulse a precursor in. You purge the precursor away after the surface has fully saturated and reacted. You bring the second precursor or a plasma dose and you again purge. So practically your precursor pulses are separated by time. And normally purging of process chamber is a slower process. In spatial ALD, we have, in our case, we have a rotary spatial ALD tool where we have a precursor zone and a plasma zone or a second precursor zone. And we are, instead of removing the precursor sequentially from the chamber, we're bringing for the sample from the precursor area to the plasma area, and we're keeping these with gas flows and clever pumping separate. So moving the substrate instead of removing the precursor and plus our precursors and purging.
Thank you.
Mhm.
Also, Darren, you mentioned quite popular processes, ALD and magnetron sputtering. There is also a process in between, and we have photonics to talk about, to say a couple of words about their PARMS technology, which fits pretty well in between the two. Vitaly, how are you doing? And tell us where is PARMS on this scale?
Hello there. Hi, many thanks. So the couple means, yeah, we developed our own PARMS coater and PARMS technology. We do so-called long-through spattering. In short words, we're trying to combine the qualities of IBS and the qualities of operation. I mean that we have very nice quality of oxides we make as a film. We have very good speed almost as evaporation.
Do you maybe have a slide, Vitaly?
Bro, give me a couple of minutes, I'll find some.
Okay,
Or I
maybe
can
later.
send the specific presentation to everyone interested in. And we have almost IBS quality of the film, and we have much less stress in the film than IBS.
And you also use the optical monitoring from OTF.
Yeah, we develop our own optical monitors, and yeah, we use a lot OTF and OTF libraries in our optical monitors.
Definitely. To everyone interested in the PARMS, please let us know and we'll connect you directly and send you more information about it. And yeah, since we already had covered a little bit of the characterization, quite a lot of the design and on the equipment, I'd like to introduce the next speaker to the room, which uses all of it and has definitely an input how everything can be a little bit better or a little bit more optimal. Stefan from Edmund Optics, you're in.
Thank you. Pull up my slide. Yep. Yeah. So I wanted to briefly discuss Edmund Optics, just what our perspective is to make sure people understand where we're coming from. Hopefully you're all familiar with us as a catalog company, but interesting enough, actually more than half of our business is in manufacturing. And in that we have 9 global manufacturing sites that have 4 sites with coating chambers. Those coating chambers cover all the technologies that we discussed, including also DLC. So we see the spectrum of these technologies and the different applications for each one of those. And this is kind of to give you an idea of what our perspective is on coatings and thin film coatings. So I prepared some of the applications that we've seen driving developments in thin film coatings. We've mentioned and discussed, I think, a lot of these. So I think it's maybe worth touching just on some of the things that haven't been mentioned yet. I think laser fusion has definitely taken a lot of interest. There's a lot of high power, high energy requirements there, which we did kind of discuss in the IDS discussion. Life sciences, we brought that up as well, the signal to noise, those narrow blocking bands. Quantum, I don't think we've heard mentioned here yet. We're seeing very high precision requirements for quantum, low loss, which we have discussed, and some new wavelength regimes. So that's within the existing wavelengths, but specific wavelengths, laser lines, atomic transitions that maybe have been less popular before. Free space optics, I think we discussed a lot of that. And then semiconductor, that's, I think, not been brought up a whole ton here yet. What we're really seeing a lot of development in is not necessarily in the lithography or like the 13 nanometer side of things, but more towards the OLEDs, micro LEDs, that type of processing in the 257, 266 nanometer type of range. And for all these applications, some common trends that we're definitely seeing is supply chain stability, geopolitical sourcing choice, and then cost pressures, as always. So common trends that we've been seeing across these are wavelength shifts. So we're seeing a lot more demanding requirements in the UV side of things, but as we mentioned and Essent Optics showed, also expansions into the IR. So it really is broadening that spectral range that we've historically seen. The lower loss, higher blocking, higher reflection across a lot of applications, which included those free space communications, also in life sciences, sharper cutoffs. Again, these are things that we saw in that metrology. The environmental robustness, this is one I think really worth mentioning. We did mention the space, but things like radiation hardening, temperature, humidity, and more stringent stability requirements. And then finally, from our integration perspective, integration and complexity. So broader band thin films, single components that are being forced to do much more. Multi-wavelength designs where you're trying to put multiple filters onto a single component or a single thin film design. So what we're doing to develop those is first more on the short term on the left side, kind of leveraging what we have, really optimizing what we have, bringing that to the next level. So it's taking those coating materials that we have or new ones, taking the designs that we have and within existing processes, within the technologies that we already discussed. Sourcing coating materials has really become an issue. So we're trying to explore alternative coating materials, seeing where else we can find them, see if there's more sustainable alternatives. We're also exploring non-conventional coating designs instead of the historical quarter wave stacks, things like nanolaminates, seeing what we can do there to improve. And then process optimization for improved uniformity on large optics. If you're talking about free space optical communications, some of these get relatively large and they need to be with those extreme low losses uniform over that entire aperture. And then finally, to really address the cost pressures, but also the precision, it's process automation and optical monitoring. On the longer term, we're discussing things like, and if you see there, I mentioned ALD, so the deposition technology. While we continuously improve the existing technology, what new technologies should we be applying? Different variations of sputtering, using glancing angle deposition, all these type of developments. So this is what we're developing internally to try to address those market needs that we discussed. And I'd say that the biggest thing holding us back is metrology. And that's been discussed here again a fair amount. There's some things I don't think I've seen really come up that I'd like to highlight. One is the UV durability. So we're really seeing customers have issues with UV components degrade more rapidly than is acceptable for them. And unfortunately, this is a very time and resource intensive thing to measure. Predictive capabilities aren't doing so well, so we're working to try to advance that, but that's where we could use some help. Laser damage, I think we discussed a bit, but I think highlighting the difference between the different pulse durations, CW versus femtosecond, that's important there. And then group delay dispersion, I did want to highlight for ultrafast. Measuring that is not easy. Doing it in a production environment is not easy, and doing it with low enough noise is also not easy to do. And then before getting to questions, just kind of a quick wrap up here. So we're really seeing that the application demands are outpacing what we're able to provide right now. Loss and metrology are what are limiting us nowadays. And getting progress within Edmund and the industry really requires us to develop materials, find talent, and standardize some processes and metrology.
Thank you, Stefan. So you've heard already with quite of some technologists. So what would be your challenges for them, or like how can they help you? Because you mentioned metrology is especially critical. So would you say that if you can, if you could make a biggest improvement somewhere, that it would be metrology that makes the most sense or the most will affect the most the final product?
Yeah, for sure. And I think the two bullets I have there are the ones that matter most to us right now. Space qualification, I think we need some help with standardization, definitely with costs and availability of that testing. And on the UV side, it really is also making sure there's some standardized tests out there, some protocols, and then reductions in cost, because running a UV laser for 3 months on end to test one component is not a cost-effective manner to get there.
What kind of the tests do you need for the space optics? You've mentioned already like UV tests, but then durability, I guess, temperature variations.
Yeah, you need temperature variations, radiation hardening, vacuum testing, all those kind of things together then combined.
Okay, I think it will be a great call to partners. So whoever is able to supply this type of the testing definitely will have a need to work with Edmund Optics. Darren, a question from your side. You also mentioned challenges in the space optics.
Sure. I was just going to add and maybe go just a slightly different direction with the chat here. Like what you notice is that almost everything we're talking about so far is kind of UV through the near IR. With even space, right, is kind of near IR telecom band 1.5 to 2 micron ish ranges, right? All the typical telecom bands. In that range, oxides work really well. And you even see that with the spatial ALD applications that Yanni mentioned. Like a lot of spatial ALD is headed in sort of that oxide direction. What the industry has been lacking for a very long time is alternate technologies for non-oxides, right? Because when you go into the deep UV or you go into the infrared, it's not oxides anymore. Those materials don't transmit in those wavelength domains, and you're sort of stuck with using some of the older technologies like evaporation for fluoride, sulfide, selenides, right? All these materials that I think we would love to not have to use, but we do. So I'm curious as the rest of the speakers talk. If anybody has knowledge or thoughts on how do we take some of these core technologies and move them in that direction, I think that's really important, especially as you start to see more semiconductor metrology happening in the VUV, right, which is now sort of in that lower than 190 nanometer wavelength domain, and almost all, we didn't talk about it here yet, but almost all defense applications are in the infrared, or at least multispectral. So I think those things are all important considerations.
Stefan, how about Edmund Optics and your endeavors with non-oxide materials?
Yeah, I think that's absolutely right. So we're investigating those as well and trying to see where we can apply them. I think indeed in evaporation is where we're seeing the most success in being able to do so. But being able to apply those to the more novel or newer coding processes would be beneficial. I don't think I would say we've made much progress on that. So that is something we could use partners with.
We have actually a comment from the chat from Alexander Tafel. Alex, you have a comment? Maybe unmute yourself and to voice your question, comment.
Yeah, sure. As I've mentioned in the chat, we have test facilities that we use for the automotive industry where UV or at least sunlight exposure is an important topic. So we have standardized test methods that we apply to test materials, whether they can handle the radiation or not. I'm not sure how applicable this is to your use cases, but if you're interested, we can discuss and see if we can use our capabilities to test some of your materials and see if we can find some relation between your long-term laser tests and our shorter radiation tests. If there's correlation, that might be useful.
I mean, automotive industry is notorious, right, for having extremely strict requirements on the environmental testing. So I think next to after the space, you're the second most advanced.
Yeah, and that would definitely be of interest. Yeah. We'd have to take a look at the different UV regimes and the pulse durations and the intensity, so to see what parallels there are and what we could reuse. But it's a conversation worth having.
Yeah, one thing I would say about UV, right, is we often see the problems in the UV and deep UV happening because the power levels are being turned up, and what that means is that we're getting non-linear issues, right? So you're starting to see things like we saw in the old days of color centers and all these sort of second order effects where you start to see material property changes in the coating materials as the power levels increase, certainly at those lower wavelengths.
Yeah, that's for the femtosecond lasers for sure. That's what I would expect as well. But at least for the CW, it might be a worthwhile trial.
Mm-hmm. We have actually another specialist in testing and research collaborations. It's a research. So Marcel, you've heard the challenges, especially for the testing requirements. Can you help? Let us know, please. You're welcome to the floor to share what research is capable of. And yeah, maybe how about the UV testing here?
Yes, thank you very much. You can see my slides, hopefully.
Yes, crystal clear.
So to give you a little bit an overview about research, we are a research institute in the Rhine Valley in eastern part of Switzerland, focusing on mainly two topics. One is optical coatings and characterization, which I will deep dive a little bit more in the next slide. Besides of that, we do quite a lot of ultra-precision manufacturing, like diamond turning, milling, ultra-short pulse laser manufacturing. So various materials from glass to metals and so on. So here we may have a little bit overlink with what Darren mentioned in the beginning about freeform optics and stuff like that. So accuracies in submicron range is very good surfaces, and also focusing on special materials like hard and brittle materials, which are difficult to manufacture. Our digital innovation lab is kind of a crossover topic, supporting the other two groups with simulation, modeling, data science, and stuff like that. But as we are here in the advanced thin film coatings, maybe having a little bit look on optical coatings and characterization. So we heard a lot about low loss coatings, and that's one of our main topics we're focusing. So using IBS coating machines, producing low loss coatings, and having many equipments available to test these, starting from laser induced damage threshold to cavity ring down, absorption measurements, scattering, and so on. So combining design to production to characterization. Unfortunately, coming back to your question, we don't go down to UV much. So yet looking into it, but are not there yet. So, and what we basically do, and this is true for optical coating as well as for the ultra precision manufacturing, we do research, applied research, so working always very close together with the industry. We are here to support the industry, but also producing prototypes, doing feasibility studies, and working on new materials. Like here you see the example of ultra thin ITO coatings produced by IBS, which is not really typically in the industry, but works quite well, and is opening up new applications. If you can go down with ITO layers with thicknesses of 2-3 nanometers, stuff like that, which is not achievable with evaporation or sputtering processes typically. And the other technology, we also heard about ALD. So we are also looking into what we can do with ALD technology for the optical industry. That's kind of the second field. And here we also go into topics like fluorides, nitrides, which was mentioned before, addressing a little bit the field of UV optics, although we can't go down with the characterization yet to that field.
Mm-hmm. So some of the challenges mentioned for the characterization, how could you help, Marcel?
Yeah. I mean,
characterization, testing, something like, or maybe some other new capabilities you're thinking of coming up with.
Yeah, I mean, we heard a lot about low loss coatings. So a lot of characterization we do is going into this direction, starting from the surface of the coating prior to the coating, but of course also after the coating to low loss coatings. We heard about group delay dispersions for ultra short pulse lasers, which we also do. So trying to find the sweet spot of supporting the industry with these technologies as a service, but also within research projects.
Because many people now requested UV, and you said you're looking at this, what are the challenges from the perspective of the testers, from your perspective, now those that need it, but those that have to provide it? Is it only sources, or there are further challenges?
It's hard to say for me a little bit, because I'm not in the details of the characterization lab, which is fighting with these issues. But from the current state we simply don't have the equipment for it. So starting from the sources, but also from all the detectors. So we're simply not there yet. So we didn't focus on that so far.
Well, so far, as we've heard, there is a huge interest, and we already heard quite a lot of the positive feedback from your partners from the industry. So thank you so much for your support on the all the developers. Do you work already? If you may disclose, I guess you probably work with Adrian, probably with the Tatiana. It's always a very limited, small community.
Yes, of course we do, but we shouldn't share too much about with whom we work together.
Absolutely. Well, then, thank you so much. And I would like to introduce the last speaker to the room, which is one of the newest Optica members, OPCOS. And I think it's you, Adrian, has a very interesting history because, and I believe you will comment on this a little bit yourself, because you basically started the company because there was a demand for a very specific solution and you knew how to provide it. And that's how Optica started. Of course, I'm talking about your famous work with Karl Storz, excuse my pronunciation. So tell us a little bit more about how Optica started, but also what are you up to now, Adrian? The attention of everyone is yours. You're on mute. Yes.
So that's not so easy here. Well, not using Zoom a lot. So, but yeah, thanks for asking. I'm just going to share my slides as well.
Go ahead.
And yeah, it was actually probably demand would be too much to say, but we just had the impression that we can do better when we have our ideas. Can you see my slide already?
Not yet.
Okay, sorry.
Now I see myself.
Okay.
You just click on share and pick.
We have been working with in that field of optical coatings already. Sorry, my slide is gone. That's a bit annoying now.
If you want, we can bring it up. We have Tulsi who has all the slides, and she will progress it for you.
Then please fill it up. I'm sorry, it worked.
No
before.
worries, that happens. Okay. But you can start the story.
Yeah, okay. So we had a history in optical coatings in the Rhine Valley, where we are located, close by to research as well. So and we had an idea and seen the processes in companies which are not only doing optical coatings, but doing manufacturing of optics at all. But we have been in the department of optical coatings and not always been happy with decisions other people made. So we decided to try to found our company, and we could do that in 2018, and decided to run that with evaporation chambers, so box coaters, E-beam, ion assistant, but state of the art, so top level of it with optical monitoring on the colors that we really could provide best possible coatings with that technology. So we are pressing out as much as we can. As Stefan mentioned before, you always need to find solutions on technologies which are existent and to find the best solutions for that. So we see us as a full service provider for optical coatings, not only doing the coatings build to print, but being in contact with all our customers in an early stage, because our customers are optics manufacturers and not always pros in optical coatings, and sometimes it's useful to have a talk to them in an early stage to avoid problems you could get while coating, after coating, while cleaning, characterization, all those topics we have discussed. You need to be aware of, and I feel quite familiar in that round because a lot of speakers we have been in contact to, so we could really also share a good experience with OTF and Tatiana. That's a great software for us. We have been in contact with Research, which is a good supplier of analytics as well. And we are using a spectral photometer of Essent Optics highly recommended.
Well, I knew everyone is connected. And next slide.
So yeah, what we do is we said we need to have machines on a high level, and also the environment should be great because we wanted to be on a top level. There was a demand. We could see in our market analysis there are some high level companies around and some with a bit lower level, but other advantages. We wanted to be very quick in responsive time and flexible when customers are coming to us, and do developments fast and reliable. So we have, in the past 7 years or 8 now, we have developed more than 250 processes, actually each one for our customers. So we do not have a list of processes you could choose. Our customers are coming and saying, hey, yeah, we have that topic, we need it on a, I don't know, on a lens strongly curved. Do you have a solution for that? And then we see what is possible, and we develop our own processes for that. So on the slide, you can see a selection of our coating types we have. Of course, we do anti-reflective with very low reflectance if needed. So we can even guarantee 0.02% over the whole range of our big machines, which is an advantage comparison to IBS, for example, which that is not really a problem to coat or to produce, but in the amount we can fill our chambers, it's an advantage on that part. Then,
Adrian, first of all, welcome to Optica. Thank you for being a new corporate member. What is the largest dimension you can actually coat in your chamber?
Yeah, the largest dimension for one piece is at about 300 millimeters. It depends a bit on the requirement, but the surface, it's a Bühler machine, an APS 1100, which is quite big. I think most of people know what I'm talking about. So yes, we can load a lot of parts in that machine.
Thank you very much, Adrian, and thank you very much, everyone. This meeting has been a way for us to show how Optica members connect to each other. And we couldn't have done this without, of course, our sponsor today. Thank you very much. Also, our keynote speakers, Darren from IDEX and Edmund Optics also featured. Our idea here is that we keep using your platform to connect. Thank you very much, everyone. And allow me to say goodbye the way that we always like to say goodbye, which is with a beautiful video song.
This is Optica. This is lighting redefined.
All right. So first of all, allow me to ask my IT department to cut the live stream. This becomes a private meeting of the minds now. We are not in YouTube anymore. And well, first of all, Darren Burns,